Hi there! This video series is to display my problem-solving and learning abilities. I plan to show that I can solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. Currently, I am learning Python. I have no professional experience in the language and have only been learning it since mid-January. My only formal training is completing the Python for Programmers course on Execute Program. While I'm picking Python up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 34th Project Euler problem from start to finish, vocalizing my thought process throughout. As always, I link to Project Euler and my repository in the description. Let's dive in. Problem 34 is digit factorials. 145 is a curious number, as 1 factorial plus 4 factorial plus 5 factorial equals 1 plus 24 plus 120 equals 145. Find the sum of all numbers which are equal to the sum of the factorial of their digits. So, the hardest part about this feels like not knowing how high these numbers go. And then there's a note here, as 1 factorial equals 1 and 2 factorial equals 2 are not sums, they are not included. Feels to me like that means no one-digit numbers, so we can start with 10. I kind of arbitrarily feel like we go up to 1 million, and just stop there, see if that's the correct answer. Let's see. And then I am going to do Python, calculate factorial, and it looks like there's a math module. So I'm going to go ahead and use that. But let's get started with creating our new file. And find the sum of all numbers which are equal to the sum of the factorial of their digits. And almost forgot to do my little date time input. I like that because it makes me know for sure how long it takes. I don't love guesswork. I'm gonna go ahead and do a limit equal to 1 0 0 0 0 0 0, so that is 1 million. And then I'm gonna say total is equal to 0, and at the end of this I am going to print total. So for in range 10 limit, and I'm going to say is special n, then total plus equals n. Can never remember whether plus equals is a thing in Python, so I feel like that's not necessarily the best function name because it doesn't really tell us anything. Going back to Chrome. I'm gonna say is digit factorial instead, because that seems like a better function name. And then just gotta define it up here. Def is digit factorial That takes in an n, and then I am going to do, let's see, for dn string n, I think. Here's where I pull that math function back up. Okay, so import math, math.factorial. I'm just going to say factorial equals that. Or, what am I doing? I can just say sum plus equals. And then I just have to return n equal sum. Okay, let's back this down to just 1,000 real quick. I'm not sure why I have that spacing there. And just see, does this work the way we want it to? Okay, so 145, which might mean that 145 is the only one in that range. Let's put our 3 zeros back there. Okay, so that's 40730. I'm gonna go ahead and do not pint. Checking in. Print. Found sum of sum. I made it too big. Take this back down to our 1,000. Okay, I did not think about how that would be so many numbers. I'm gonna make this a little different. Actually, 999. 9 factorial. That seems obnoxiously large. Really? Okay, cool. So 362,880, that times 2, and then plus, what are we looking at? 999. Should have done the plus 2. Clear, clear. (108,8640). 108,8640. So it seems like our algorithm is working and giving us like what we want. So let's go ahead and delete that. Okay, so for 1 million, it's 40730. Let's go ahead and bump it up to 1 billion and see if we get a different answer. I imagine at a certain point, it just becomes impossible for this to happen, but I'm not 100% certain. And now that we have bumped it up to 1 billion, it is taking a somewhat longer time to run. So, let's go ahead and check our algorithm here. So really all we're doing is we're just very basically, naively going through the entire list of every number and individually checking whether it is a digit factorial. Could probably cut this down quite a bit by saying if sum is greater than n, return false. I obviously did some Java coding. So this one is taking a bit too long to run. Let's go ahead and cancel that. Go ahead and try it again with this little catch that should reduce the complexity. Go ahead and let that run for a few seconds at least, maybe a couple of minutes. It's possible that using this math.factorial is slowing us down quite a lot. It's also possible that there's a much easier way to go about finding these numbers. I'm thinking they're quite rare, given that there's only one of them in the first 1,000 numbers, or first 10,000 numbers. And maybe we've just gone too high with this limit of 1 billion. I'm curious whether, well, I'm not going to scroll up through 10,000 numbers, but giving this another little bit here. Okay. I am losing patience, but that is okay. So, it's all numbers, which doesn't give us very much of a good idea of, like, the upper bound of this sort of thing. Okay, I'm gonna go ahead and cancel that. I'm gonna bump this down again. Let's see. So, let's do 10 million. We did 1 million previously. And that finished in a couple of seconds, so 10 million should also finish in a relatively short order. I would think. Okay, so that is 40,730. Let's run it again with the smaller set. I think that's the number we got before, and it is. And then I'm going to go ahead and run it with the slightly larger number. As you can see, when we ran it with the 10 million, we're now running it with 100 million. Though we got the same result from 1 million as from 10 million, so I'm pretty confident that this is going to be the correct answer. And it is. So, other than just broadly guessing, I'm not entirely sure how we're meant to say, like, oh, it's definitely all the numbers under this. Or all of these numbers are definitely under this amount. So, it is unclear to me exactly when you know. But Obviously, even running it for 10 million, we're well within our time limit. For 1 million, it only took a couple of seconds. And we had a pretty straightforward algorithm for finding this, I think. Especially with the, use of math.factorial. We could have wrote our own factorial finding function, but when it's trivial things like that, I prefer to use whatever is built in rather than reinventing wheels. I'm not trying to learn how to write a program that makes factorials. I am trying to learn how to problem solve better. So, I would say it's still taking just monumentally longer for the more zeros we add on this. So I'm going to cut this down to the 10 million before I commit here. But I'm going to call it there for today, and I'll catch you in the next one.